Okay, thank you so much for the invitation. It's a real pleasure to be here with you today and after Malion's talk. Today I want to speak about some work that I've been doing during the year about information theory. And we will touch on multi-layer and simplicial complex, but also I will speak about a recent work in which we have taken a different look at some maximum entropy approach for modeling networks. So networks, like the internet, they are networks that think in the sense that they make distributed computation. And another example, significant example of this case are neural networks, which perform some tasks and are able to predict answer to questions. And then there are, again, a network that think themselves like the brain. So one of the burning questions in complexity is whether there is a unique framework to characterize the complexity of both types of networks. And here in this talk, I would like to discuss how, whether networks and information theory can provide the foundation for this emergent field. And in general, I think most of the network can be classified in two classes. So network of physical systems, so like the brain, the interaction of the cells, social network, and network as, you know, a computational tool, so neural network architecture, substrate for message passing algorithm, and so on, that perform distributed computation. And then there is a world of actually networks which are very interesting that live in the middle of these two classifications, like the World Wide Web, the internet, but also social online network and financial network that have both a computational and a real kind of interpretation. So machine learning is usually thought to be, argued to be a black box, but there are some principles that are emerging that are at the foundation of its effectiveness. And one is the information bottleneck principle, and also another one is the relation with the renormalization group. And in network theory, also information theory is fundamental, but the topics that is used most of the time in order to model network is maximum entropy principle. So here we would like, in some sense, to have a framework that merge these different approach of information theory for these two types of networks. So in the information bottleneck principle, one is given a signal and a code book that, or an encoder that codifies the signal, and then an output. And the problem is to choose the best encoder, the best code book, which is compressing the signal, but encoding the necessary information which allow to generalize. And the encoder is defined according to the information bottleneck principle by maximizing the difference between the mutual information of the signal and the code book minus a Lagrangian multiplier and the mutual information between the output and the encoder. So in maximum entropy principle, which is this other very important principle, one instead has a problem of modeling data, and one wants to have models that are least biased given a set of constraints. And this approach has been very popular in different fields, including urban and regional modeling with the early work of Alan Wilson in the 60s, biology, computer science, and economy. And actually, this is the tool that is most popular in network science, in which, in order to model a network with given constraints, you assume a probability measure in a space of all possible networks. And the network have a given number of nodes, and then they are completely arbitrary. And then you define an entropy, and the entropy characterizes the information content in your ensemble. So the logarithm of the typical number of graph that you have in the ensemble. So there are two types of constraint, the hard constraint and the soft constraint. So the hard constraint is where you impose that all the network of your ensemble satisfy some constraint, you know, total number of links. They all have the same total number of links, or they have the same degree sequence, exactly the sequence that you want. Or there are soft ensemble in which you allow some fluctuation. So you fix in average the total number of links, or fix in average the expected degree of each node. And if we look at the heterogeneous ensemble in which you fix the degree sequence, in one case you have the configuration model in which you have stubs on each node indicating the degree that the node will have, and then you match the stubs. Or in the canonical ensemble, you have also this exponential random graph in which you fix in average the degree of each node, and then, you know, you draw a link with a given probability Pij that is the marginal of this exponential distribution or Gibbs distribution. So these exponential random graphs are very popular. They have been used in sociology. So they can be generalized to have not only constraint on the degree, but constraint on other variable. But in general, they always lead to a marginal. So the probability that a link between I and J is there, which has this form, this kind of logistic form, and the physicists recognize in the form the Fermi-Dirac distribution. And this is interesting from the physical point perspective, but also for the network scientists is quite interesting because it implies that this probability Ij is not factorizable into term only depending on I and only depending on J, but it has some correlation when you cannot neglect this exponential at the denominator. And then this correlation leads to degree correlation, and also called natural correlation in the network with expected degree sequence. And the entropy, when you maximize the entropy, is given by this simple expression. So for the microcanonical ensemble, instead you ask that each graph satisfy a given constraint. So the probability over the graph ensemble is uniform over all the graph which satisfy a given constraint. For instance, in this case, a degree sequence. And an important quantity is the number of graphs that satisfy this constraint, which is also called the partition number Z. And when you have the entropy of this ensemble, which is this measure of, you know, the information content of the ensemble, you find that the entropy is the logarithm of this number. So it's simply the logarithm of this number, and this is the famous Gibbs expression for the entropy. So how these ensembles are related, how these entropy are related in the soft or in the hard constraint setup. And they differ by a quantity which is called omega, which actually calculates practically as a measure of the distance between the ensemble with soft constraint and ensemble with satisfied the hard constraint. And is the logarithm that in ensemble with soft constraint, the hard constraint are exactly satisfied. Now, in physics, usually this term omega is negligible, but in network there is one important thing, that this omega actually can be quite large, of order of the number of node n, and so cannot be neglected. And this means that these two ensembles are non-equivalent, and these has consequences. For instance, for dynamics, if you look at epidemic threshold on a network with hard constraint and on a network with soft constraint, these are different. And an example, for instance, if you fix every node of having a certain degree, for instance, degree 3, then you have a regular graph which has a given epidemic threshold. If you fix every node to have in average the same degree, so for instance 3, but in average, then you have a Poisson graph that has another epidemic threshold. So from this expression, you can also get a famous formula, which is called Bender-Canfield formula, which is the number of graph in the ensemble with given degree sequence. So we generalize this to generalized network structure, and Maglio has given a very interesting overview of the field of multi-layer network, but there are also simplicial complex that are capturing many-body interaction between the node. So in multiplex networks, if you have two layers in which there is, an email and mobile phone communication, any two nodes are not just connected or not connected, but they can be connected in different way. And the way to characterize how they are connected are called multi-link. So they can be connected in layer 1 and in layer 2, only in one layer, all in the other layer, and so on. So in reality, many multiplex networks that one studies has a lot of multi-link one-one. So has a lot of multi-link in which two nodes are connected by more than in more than one layer, and this is a kind of challenging if you just model each network independently. So what we propose is to consider the multi-degree, so the number of multi-link of a given type incident to a node, and to construct ensemble with given multi-degree sequence. So you have stubs that are like the red stubs living in both layer, or like the black or the green stub living only in one layer. And then you do the configuration model by matching the stub of the same color. And you can do the statistical mechanics approach. Again, the marginal is the probability that I and j are connected by multi-link vector erm as this not factorizable Fermi Dirac distribution, and only if the degree are not too broad, the degree distribution is not too broad, so there is a maximum cutoff of the multi-degree sequence, then you can have an approximation of the marginal, which is factorizable. The entropy, again, you can have the soft constraint or R constraint on the multi-degree. The entropy are different, and they differ by an extensive quantity. So again, when you have an extensive number of constraints, so you fix not just the total number of links in the network, but the degree of each node, and these are n constraints, the constraints are extensive, and then there is this difference between the microcanonical and the canonical ensemble. For higher order network, also these are structures that are very important to understand a variety of systems. And higher order network are another generalized network structure, which is not only formed by node and links, but also triangle, tetrahedra, and so on. And for higher order network, you can define generalized degree again. And here, the generalized degree of the node is the number of triangle, for instance, incident to a node alpha, but you can have also the number of tetrahedra incident to a node alpha. And we propose in this article by Cornier and Bianconi the configuration model of simplicial complexes. So what we do is we place a stub on the node, and then we merge the stub, but not pairwise, but we merge it in a way that we form triangle or we form tetrahedra, and then from this structure we can construct the simplicial complex. And for simplicity, we start with a model in which, only simplices of one dimension are allowed. So for instance, only triangle or only tetrahedra. And the marginal, again, we have this Fermi Dirac not factorizable structure, but if the degree the distribution is sparse enough, it factorizes with this non-trivial generalization of the previous formula. So we have a code. So we have done the statistical mechanics. We have a code available in GitHub for this model, and we can also play the combinatorics and have an expression, this ugly expression for the number of simplicial complex with given generalized degree of the node. But here each term can be interpreted in terms of this matching of the stubs. So there are two things that I want to add here. So many people that work with simplicial complexes do this operation. So they look at a model formed by triangle, tetrahedron, and so on. Then they just look at nodal links, and then they do the clique complex. So every clique becomes a simplices. So if you have 3 nodes connected pairwise by 3 links, then it becomes a triangle. And if you have 4 nodes all connected to each other, it becomes a tetrahedra. But this operation, when you do this operation, you are not given for granted to obtain the original model. And you can see this quite neatly if you start with a network, which is a simplicial complex of dimension 1, only node and links. There are no triangles, but you start with a network, which is scale-free. And then you see that the number of cliques in this network is actually diverging with the network size. That means that if you do the clique complex, you will have very high dimensional simplicial complex. So again, this operation is something you should be aware, and as it happens like this for a network, it happens like this also for higher order simplicial complexes. The other thing that I want to say is that until now we spoke about pure simplicial complexes, so only working with triangle, only working with tetrahedra, but actually we can go and use this to model hypergraph very, very easily. And the only thing we need to know is to have a multi-layer approach. So we start with the first layer, which is a pure one-dimensional simplicial complex, is a network. Then we have a second layer, which is a pure two-dimensional simplicial complex. We can add a third, a fourth, which is higher order dimensional simplicial complexes for, working only with tetrahedra, only with simplices of higher dimension, and then we aggregate. And what we have in the aggregate is the hypergraph, in which we have any type of simplices of many-body interaction that we want. Okay, so this is a simple model to go from a pure simplicial complex to a hypergraph model. So there is no much fear to go from one to another one, although many people just claim that there are big differences, but combinatorically there are not. So if you want to have more information, I make a small advertisement of my book by Oxford University Press on multi-layer network, and my soon-to-be book in Cambridge Element on higher order networks. So let me now stop with this, traditional approach for statistical mechanics, in which you get this typical Fermi-Dirac marginals or logistic marginals, and ask from a physicist point of view, what are the ingredients that are responsible for having this kind of quantum statistics? So the Fermi-Dirac distribution is known to be the distribution of quantum particle, the occupation number of quantum particle in a Bose-Gas. But why do we have this? So the assumption that we are making is that a graph is only specified by its adjacent symmetrics. So we identify the graph with its adjacent symmetrics, and we treat every link as unlabeled. And we impose that every two-pair node is either connected or not. And this is exactly the assumption that in physics lead to the Fermi-Dirac distribution for the occupation of energy level of a Bose-Gas. So can we get rid of this assumption? Can we try to have a classical model of network without this quantum statistic? And yeah, and the answer is yes, we can do that, and we need to get rid of what are these quantum hypothesis which entails allowing multi-edge and considering links as labeled. So practically what you would do is to think of a network as a set of links and an edge list. Okay, so that somebody can, send you the information about the network by sending the information about each link, which node are connected to each link. So a link is can be, when somebody sends you a message that is a link of a given network, what this message content will be the pair of nodes connected by this link. Okay, so the network will be now given the probability, instead of having a probability of an adjacency metric, we have the probability of an edge list. And the entropy will be just constructed with this probability of this edge list. And if we have, and every link has the same probability to connect to I and j than any other link. And if we fix now that the network has a given degree sequence, expected degree sequence of each node, then the marginal becomes a marginal given by this expression, which is factorizable from the beginning, because we are getting rid of this quantum hypothesis. So we have finally a marginal that is factorizable into contribution regarding node I and node j. But as this denominator, which is k average n square, that is rather unusual. And only if you consider the probability, the expected number of link connected I and j, you have practically the uncorrelated network ensemble expression with k in the denominator k average n to the power of 1. So we can construct the entropy of this ensemble, and the entropy gives us the explicative power of the ensemble, and this entropy depends only on the degree distribution now. So we can look at this entropy, and we can look, for instance, at different distributions. So we can consider scale-free distribution and look at the behavior of the entropy as a function of the exponent. And we found that if the distribution becomes broader, gamma is go toward 2, the entropy decreases. So it seems contradictory that, that there might be, there is a debate about this, but many networks in the range of gamma between 2 and 3 in some sense, or, with broad degree distribution, and this might correspond to a small entropy. Okay, so we will get back to this question. And in general, there is even a more significant question now in all this maximum entropy ensemble for network. And this is, okay, well, maximum entropy gives me the least biased null model given a set of constraints, but there is one question that remains unanswered, is where does this constraint comes from? Okay, so this maximum entropy principle cannot justify where the constraint comes from. If there is a complexity, if there is a non-homogeneity in the graph, this in the latent variable, so in the variable that I'm constrained for, and I mean this is something maximum entropy cannot give me a clue of where why this heterogeneity is present in the real network. So the question is, can maybe another information theory approach explain the emergence of heterogeneity in real networks? And here we go back to this idea of having a source, an encoder, and a receiver. And the source now will be the source of the network, the edge list. So every link will be indicated by the pair of 2 connected nodes, I and j. The encoder, we just take the feature of these two nodes, for instance, the expected degree of node I and the expected degree of node J, and then we will have a receiver. So if the encoder practically erases information about the node label and only retains the degree, the expected degree of the node, we are actually sending to the receiver a message, a set of messages that encode for a compressed representation of the network, in which we don't have the node identified with the node label, but we have some super node identified with the expected degree of the node. And for this compressed ensemble, in which instead of having for each link, having the node label, we have for each link the expected degree of the connected node label. Then for this ensemble, we will have another entropy, the entropy of the compressed ensemble H. And interesting, since this compressed ensemble is erasing information essentially about the identity of the node, this entropy of the compressed ensemble can be seen is equal to the mutual information between the source and the encoder. So this is a particular property of this kind of encoder. So what we do is what is called in information theory finding the optimal input distribution. Here we want to find the optimal degree distribution such that we maximize H, the mutual information between the signal and the code book, minus lambda S at a given value of the entropy of the source. So if we do that, what we find is that the degree distribution that we get, the optimal degree distribution, has a power law form with a cutoff for small k. Okay, so for small degree as the given degree cutoff. So what happens is that there is a trade-off between the entropy of the source and the entropy of the compressed network as a function of this Lagrangian multiplier lambda. And so that when the source is highly informative, then the compressed model is as a higher entropy and so on. They are correlated. And this explains in some sense the emergence or the information theory advantage of having a very broad degree distribution, a power law degree distribution. We did that and we extended this also to spatial networks. So because node in space, that these are the airport network, they are not distributed uniformly. So here one question is also, for instance, for network embedding, what is the best prior for position of node into space? Is this a uniform prior or should we take another prior? And in order to tackle this question, we consider, node embedded into space, so node I and J at distance delta I and J. And we characterize this distribution of node in space by the spatial correlation function, so the distribution of point at distance delta. And then we consider an ensemble, spatial ensemble, in which we fix in the network the total cost of the link. So we assign to every link a cost f of delta, which can be either linear with the distance between the node delta or linear with the order of magnitude of the distance in the network, logarithm of delta. And then we want to impose as constraint that the total cost of the link is fixed. Then in this ensemble, the marginal is given by this expression when the cost of the link is linear in the distance, the marginal decays exponentially with the distance. When the cost of the distance is linear in the logarithm of the distance, the marginal decays like a power law. So this will be the classical ensemble under consideration with a given entropy, which will depend, of course, on f, on the marginal, and on the distribution, the correlation, pair correlation function. And we can ask again, what is the optimal spatial correlation function, omega delta? We use this picture in which now the encoder only sends the message about the distance between the two linked nodes. And by applying our principle, optimization principle, we find that this omega delta, it depends on this marginal and is given by this expression. So if, for instance, the marginal decays like a power law, omega delta is again a power law of the distance, now positive power law of the distance, and this implies that the distribution of node in space is fractal. So again, we have the heterogeneity, emergence of non-uniformity, heterogeneity in the input distribution of the latent variable. Finally, we consider an ensemble in which we fix both the expected degree and the cost of the link at a given distance. The marginal read in this way. The encoder now sends, the encoder erases the information about the node label and only keeps the expected degree of node 1, the expected degree of node 2j, and the distance between them. And we see that actually the optimal correlation function is given by this expression. Note that this expression here, you have a power law of lambda, but it depends on f of delta. So f of delta can take different form, can be a power law, can be an exponential, can be very general. But this function is only a function of this combination w of k, k prime, and f of delta. And what we have done in this paper which we have published this last year with Radicchi et al. Is that we have looked at different airport data sets that have very different f of delta function. But then we have seen that this pair correlation function obey the scaling with this W, that is the predicted scale of this optimal distribution. It doesn't need to be like that, but it's interesting that it's like that in this case. So it means that the network are in some sense optimized in some way. So this concludes my talk. Sorry if I'm running over time. So I wanted to discuss you that information theory is essential to model simple networks, multiplex networks, and simplicial complex. And there is this new take on information theory of network that can give an explanation of why non-uniformity is so ubiquitous in data. Thank you so much for your attention. These are the paper.
Thanks, Professor, for the talk. So in the interest of time, we will just take one question for this talk. And I request all the other participants to post your questions during the break session. So Deepak Maurya has a question now. So over to you, Deepak.
Yeah. Thanks for the wonderful talk, ma'am. I just had one question about the representation that you have used for simplical complex and the hypergraphs that we usually do in the ML literature, where it is represented as a tensor when we connect only when an entry in a tensor is non-zero only if the nodes are connected with a hyperedge. How does it compare to the representation of simplical complex?
So if I understand well, you say, the hypergraph, you just have one connection with one hyperedge, and the hyperedge can have a connectivity which is a variable, right?
Yeah.
So practically the hyperedge is a higher order interaction of, including M node, right?
Yes.
With M greater than 3. And a simplex is the same thing.
Okay.
Is the same thing. So a simplex of dimension 2 includes 3 nodes. Okay.
Okay.
So what is different is the simplicial complex. The simplicial complex is different because mathematician wants to include all the phases, all the subset Okay.
Yes.
But if you consider just at the combinatorial point of view,
Yes, ma'am.
and you have a model which generates pure simplicial complexes, so practically generates all interaction with having hyperredge of size, for instance, 3 or size 4. Okay, so you can consider, you can neglect this subgraph. You know, the mathematician like to think about the subgraph, and this can be useful for topology and things like that. But you know, in a combinatorial point of view, you can forget about this and just have a network which has interaction of 4 nodes.
Okay, ma'am. Okay.
And then you have another network which has interaction of 3 nodes, and you combine the two, right?
Yes, ma'am. Yes. Okay, ma'am.
Yeah.
Got it. Good. Thank you.
Thanks